component piece.
Good morning. I'd like to start by thanking the organizers and also the staff. They've been tremendous, and that only covers part of it. Ever since we've been here, and I came up with the term enthusiastic hospitality with a smile. That's the way I felt, whether we're at the hotel or at getting on the train. And so I told Frank Ling last night, he has reason to be proud of this fellow countryman. And I thank all the people. Okay, this is the same title I've used before, the evolution of lattice energy converter, because it is still evolving. I'm going to go quickly over the background, but I do have links to previous presentations that may have more information. But a LEC will self-initiate and self-sustain the production of a voltage and current. Naturally radioactive materials are not required. The current voltages produced are non-ohmic. Current does not saturate as the electromotive force is increased. And these results are repeatable. I think, as I mentioned the other day, John Paul Bavarian was the first one to repeat them. And since that time, there have been several people. And multiple people have replicated these gaseous-like results. And I'm really encouraged by the fact that several of the presentations here have talked about their powders, and in some cases, they've referenced the LEC. And I'm really encouraged by that. And if there's anything I can do or we can do to help in the experiments that you're doing, we'd be happy to do that. We describe the LEC as an electrophysical direct energy conversion device. It involves contact electrification, hydrogen-coated hydrogen host materials, different Fermi levels with continuously adjusting equilibration and re-equilibration. And it can be described by analyzing and considering ion drift and diffusion and stochastic electrode wall impacts. And I'll go into that a little bit. It's a simple looking device. You see on the left is just a pipe that has a pipe inside it. And the one inside has palladium co-deposited with a hydrogen included. The outside one is just a brass pipe. And initially we started by applying a current because we thought if we can ionize through gas, then we can go to higher temperatures without having to worry about higher temperatures with oxygen and hydrogen evolving. When we started doing calculation of coefficient of performance a few years ago, we realized that when we reduced the voltage we were applying, the coefficient of performance went up. So we reduced the voltage a little more, the coefficient of performance went up. You eventually get to the point where you say, well, hell, let's just turn off the current supply. We did, and we got more, but we still continue to get voltage and current. So that was the realization that, by God, this may be real. On the right, you see just a different form fit, planar selection, and in some ways it's a little easier to construct and also to maintain the separation distance. This shows a typical test, the operating regime, and what you see here is, this is the voltage. We down here across the bottom, we have load resistance. So if we start out and with real high voltage or high resistance, we get the high voltage. Basically, what we're measuring at this point is close to the work function difference between the electrodes. As we reduce the resistance, we're actually increasing the load on the cell. And when we get down to the low, say 10 ohms, when we're producing the maximum short circuit current. But at that point, the voltage is very low, and so the power is very low. So anyhow, I'll mention this again later, but it ends up being a safe device. And the maximum power output is where kind of at the midpoint between the diffusion and the drift of the ions in the gas. And one of the points I want to make, and this is another thing that kind of hit us in the head when we realized it, we're producing just under 1 milliamp of current here at the far left. And And that's 4.4 times 10 to the 14th charge carriers per second. Trying to do that with radioactive materials requires several curies of radiation and a lot of high energy particles and harvesting those. And we just don't have that. So ultimately we said we've got to find another mechanism to produce this. And that's when we came up with the electrophysical concept. So let me describe the electrophysical concept. You have electrodes with different work functions and different materials. The contact electrification and tribal electrification, Fermi levels and Fermi level equilibration that's continuously going on. Lock-Schmidt's number, 2.687 times 10 to the 19th molecules per cubic centimeter. Okay, there's a big number, and that's going to help us when we want to achieve the high currents. Maxwell-Boltzmann's equation, where the number of wall impacts at room temperature and pressure is 1.08 times 10 to the 24th wall impacts per square centimeter. Quantum mechanics, electrolytes include gas, liquids, gels, solids, solid states, and we've used all of those, and also we've used different materials, the palladium hydrogen, iron hydrogen. In fact, one of the independent replications was by Antonio De Stefano, because he had read about the LEC on Linear Forum, and we had done a little bit of work with iron. He wrote a totally independent, I was not aware that he was doing this until he published the paper. And I encourage you to get that and look at it, because it is really a totally independent and very thorough report. Okay, so these parameters include some of the big numbers that we can take advantage of. Let me talk a little bit about the Fermi level equilibration and re-equilibration. Here on the left, you see that we have the low work function electrode and the high work function electrode. And when we connect these together with a wire, they will equilibrate. The electrons will flow from here, bringing this number of electrons up, and then they will be reduced on this side. And so this is the status that you're in when you have the wire connected. At that point, everything stops, unless you have an electrolyte between. And Langmuir in 1916 demonstrated that if I had, in this case, he had zinc and copper connected right here, and in a space, and an electrolyte, and the electrolyte he was using was ionizing he had ionizing radiation that he was using to ionize particles. So with this electrolyte, he was conducting a current. And so this is what happens when you have the ions in between different materials with Fermi levels. As soon as you start conducting the current, the Fermi level equilibration adjusts. And now it's trying to readjust back to the equilibrated state. So if we can control the rate at which the current is being adjusted here and control the equilibration and re-equilibration that processes are going on, that is an important way to conduct the LEC. Here's a equivalent circuit, or this looks kind of looks like one of the flat electrodes. We have the high work function electrode, the low work function electrode. We connect the two of them through an external load. And in this case, we have a resistance box that we can adjust, put a DVM out there. It doesn't take a lot of expensive electronics to do this. And when you connect them, the Fermi levels equilibrate. From this point on, it's all involved in the electrolyte. And allow me to define electrolyte as any medium that will transfer electrons or charge, ions, anything with mobile ions or will transfer charge. And the thing we've used most is gas. We kind of started that way because, for one thing, we wanted to avoid the possibility of electrochemical reactions, which is what tripped up Volta when he was doing his experiments. He discovered that he was producing a lot of power, and he discovered that certain things work better than others. Basically, he invented the electrochemical battery. And that was not a bad invention, because that's the primary source of a lot of energy we have today. But because of that, we think the electrophysical contact electrification has probably not received the attention that it needs. So the electrolyte here, what happens is electrons, the materials would like to go back to their native state. In other words, a high work function electrode has more electrons than it likes. Low work function electrode is looking for electrons. So we've got to transfer electrons from the high work function to the low work function. There's an electric field in here, and we're actually transferring electrons against the electric field. And that's one of the reasons when in the curve you saw for the power, there's kind of a midpoint in between. And that's where the maximum power is produced. Okay, properties of the electrolyte. This is one of the areas that we're focusing on now. It's got to contain mobile ions. It can be a gas, a gel, liquid, solid state, semiconductor, and we're just getting involved in some of the semiconductor efforts. The source of mobile ions can be ionizing radiation, chemical, autoionization, thermal, mechanical, electric field. We're nowhere near the electric field you need for Townsend avalanche, but that can be a source of ions. And it must be able to transfer electrons to and from the electrodes. You have the activation energies and the transport. This is another point. We talk about activation energies. That's the activation energy for the system, which involves not only the palladium hydrogen electrode, but also the counter electrode. And so we're now beginning to focus on the low work function electrode and make sure that we don't have, that's not limiting the activation energy or how much current we can pass. I'm going to give an example for gas electrolytes because that's the one we've studied the most. The mobile ions in a gas are in constant random thermal motion. The molecules collide with each other and with the surfaces, the electrodes. Molecular collisions are inelastic. Maxwell-Boltzmann energy distribution has defined those as a function of temperature and pressure. And based on them statistics, some gas molecules will have enough energy to exceed the activation energy required to knock an electron off of the high work function or to add an electron to the low work function material. And I've added a web link here, and I've also shown this on the last slide. When we were in France last September, we had an hour-long presentation and went into a lot more detail in some of these theory, some of this information, and here's a link to it that may be helpful. Okay, here's the Maxwell-Boltzmann speed distribution for hydrogen. The blue line, these are all cold. The blue line is at 25 Kelvin, the red is 50 Kelvin, the green is 100 Kelvin. So if we're even at room temperature, we're down here, and the tail goes out considerably farther as the temperature heats up. And as it increases, there are more molecules with enough energy that they can knock things off, and we're having 10 to the 24th impacts per second per square centimeter against the electrodes. So we even though we're down by several orders of magnitude, we have a big number that we can apply to the problem. And here's the energy distribution. And now here are the temperatures. This is 25 Celsius, so we're on roughly room temperature, 250, 500, and you see how they affect it. And here's the activation energy here, and anything we can do to move the activation energy to the left increases the number of charges that we can harvest. If it goes to the right, if it increases, then that reduces the number of charges that we have. Okay, let's take an example and see how it shows up. We assume hydrogen of 1 atmosphere, 300 Kelvin. The number density of gas at that is 2.686 times 10 to the 19 per cubic centimeter. The mean speed of the molecules is 1,773 meters per second. The number of wall impacts, as I've mentioned, is 1.08 times 10 to the 24. If we assume that one EV is required to remove an electron from the PD hydrogen host material, an electron volt has 1.6 times 10 to the minus 19th joules. And if it takes 1 billion impacts to knock off one electron, that will produce about 173 microamps per square centimeter. Now, recall back to the slide that I showed that where we were producing about 700 microamps per square, or microamps. That was for about a 4 square centimeter surface area. So this is amazingly close. And you know, all we have to do if we say, well, it was really 0.68 electron volts, then that increases the number, and that's a number that's been reported by John Paul and others, and we've measured that too. So we believe that this analysis tends to confirm that the electrification, contact electrification. Okay, this also points to what we can do to increase the power. You know, electrode features including hydrogen-filled particulates. In fact, multiple people have presented their powders, and so far, every powder that we have tested, if it produces heat, it will work. It has worked for this. Now we have a very limited number of those tests, and if that's something where you can do, we could get some help from people here. Reducing the separation distance, the math says that is a good thing to do. Materials with larger work functions also helps. You know, it does it increases the voltage we have to have, electric field we have to go against when the ions are transferred, but on the other hand, it increases the number, and so it moves everything to the left. And I recall Stan Spock and Martin Flashman years ago talking about the sea of electrons in the conduction band. So when you have hydrogen-included metal, you have a lot of extra electrons in the conduction band, and perhaps that is a source of why we're able to reduce the activation energy and the source of the electrons we transfer. Improved electrolytes. We've talked about gases. We've talked about hydrogen, but we also are looking at pinning gases. We've tried a mixture of hydrogen and argon. We think maybe hydrogen and propane might be a good pinning gas. You know, you get a bigger molecule, you may knock off more electrons. So that's the central theory there. Liquids and gels, we've tested these. The big concern there is we want to be sure we aren't creating a Volta effect, which is an electrochemical effect. Solids and high temperature epoxies. It's amazing what will provide mobile ions when the temperature gets hot. And we were using high temperature epoxy for what we thought was an insulator early on, and then we discovered that it actually became an electrolyte at high temperature. Okay, so and then ultimately, if we increase the surface area, you know, if we can go from 1 square centimeter, which is what the power density we try and measure against, if we go to 1 square meter, that's 10 to the 4th, so that's 4 orders of magnitude increase. Dave Dangle asked when we were in France, is LINER involved? And I think it is, but the definitive evidence we haven't measured it, but we're using LINER-based materials that we know will produce LENR. We took the cell to Texas Tech and they analyzed the gas, and they did not detect any helium, any excess helium beyond what you would expect from the environment. Without the hydrogen host material, it's below our ability to measure, and we've discovered a patent by an Israeli company that reports a few tens of picoamps when they have a contact electrification type device. And the one thing, or a couple things they don't refer to any hydrogen included metal. They don't even refer to hydrogen, but they list several different materials for work functions that they have tried. And the experimental results indicate that we have low activation energies, and current and voltage does not saturate. And thermal energy does contribute, but where does the thermal energy come from? That could be, it could be that some of the things that you're seeing in your experiments and your powders are producing enough thermal energy that they actually can create the thermal energy we need. Conclusions, we think the model supports things. The analysis is for gas, but other electrolytes work. Device configurations similar to electrolytic capacitors have been constructed, and they produce a voltage, and lack simplicity. We think means that once we get something close to optimum, this is something that can be produced very quickly, particularly if it is in the form fit of a electrolytic capacitor, for example. And in that regard, if you have active hydrogen host materials that work for you, we'd like to try it in our device or help you to try it in yours. So thank you for your attention. Any questions, I'll try and answer, or if we don't answer them here, we can talk later.
Thank you. Any question, comments?
Did I scare everyone?
Question quite simple. Did you consider the possibility that is it's okay?
Yeah, just
Okay.
speak a little louder.
There is a possibility that some low energy electrons, like by emission, coming out from the electrode, and is the reason?
Okay, you're saying the electrons are emitted from the electrodes, is that the?
Yeah,
Okay, yeah, when you,
like bad emission, but very low energy.
we'll take them any way we can get them. Ed Storms talked about them, and his, I think a lot of those were in the bulk. I don't know how many of those actually will make it out of the surface, but we'll take any electron we can get. Conrad?
Yeah, thank you very much for your presentation. I think the model you have presented is really nice, and you can explain many things you have measured. My point is that you can use, for instance, I think low work functions materials as a surface of the, and then you can get, because at very small angles, the molecules contacting the surface, they don't need exchange of the electrons can happen at very low energies. You don't need one electron volt for that. So this the method that you can increase the power you produce or the voltage you produce. Something like this. I think.
Yeah, we are just now starting to look at things like where charge concentration might occur in the electrodes because of the way the shape of the electrode, or do we have pits on the electrode, or do we have prominent, when we put the particulates on the electrode, we're looking at that, and of course that could be a way to help increase the transfer. We kind of feel like the sponsor that the contributions to the current are coming from a few spots rather than the entire surface. And at this point, so we not only have to increase the surface area, but we have to increase the spots per square centimeter that are active.
I think atomic physicists they measured something like this. At very low energies, below 1 electron volts, and they see the different electron transfer reactions. One electron, 2 electrons can be transferred to the surface and the molecules.
Okay, thanks.
There are a lot of data out there.
We can talk over a cup of coffee or beer or something. But anyhow, thank you.
Okay, let's thanks to the Professor Gordon. Thank you.